Greetings from Hacettepe University, Turkey. My name is Efe and I am the captain of the Space Troopers team. This is the second on-site rover, Merih. Space Troopers is a rover team established in 2019. Our first achievement was in the remote category in 2023, where we secured 10th place. We then participated in the on-site category in 2024, achieving 7th place in the report phase and finishing 22nd in the finals. Our team currently consists of 30 members, including engineers and engineering students from various departments. We work within 5 different sub-teams: mechanics, electronics, software, science, and organization.
Hi, I am Mehak, captain of the electronics team. The electronics team manages the embedded system software, basic control algorithms, motor driver controls, and electronic communication process. Additionally, we design, manufacture, test, and prepare all power systems on the rover for operational use.
Hello, I am Alper, the captain of the mechanical team. Our team consists of 7 members. We are responsible for the design, analysis, cost-effective and reliable manufacturing and assembly of the rover's mechanical systems.
Hi, I'm Bishra, software team leader of Space Troopers. We are a team of 4, consisting of 2 computer engineers and 2 electrical engineers, all successful and dedicated individuals. We focus on autonomous navigation of rover and drone, dynamic systems, and computer vision.
Hello, my name is Iran and I am captain of the science team. Our main goal as the science team is to understand the geological evolution of wireless mariners, the Mars region designated for ERC 2025. For this purpose, we first conducted literature reviews. After this, we aim to examine Mars yacht with satellite photos and conduct field studies with on-site missions.
Our motivation for participating in the competition is to learn and improve ourselves in our engineering fields. Our team, which came together with a passion for research and development, continues to work to move the project forward. During the preparation process, we had only one goal: to succeed in the competition. In line with this goal, we have achieved a rapid adaptation with our past experiences, the support of our mentors, and the engineering perspectives of our new members. We are developing our project with the opportunities offered by our university and sponsors, and we aim to transfer the knowledge and experience we have gained to future teams.
The power required for rover's movements is supplied by a 6S LiPo battery. The rover's managed module and communication system are powered by 3S LiPo battery. Different voltage levels needed by components at various points on the rover are obtained using voltage regulators. Movement is achieved using 4 DC motors which receive power from motor drivers. Communication between the motors and the drivers is carried out using the PWM protocol. To control different components on the rover from a single point, serial communication protocol is used between the JSON Nano and microcontrollers. Communication between the ground station and the rovers is provided via 2.4 GHz omnidirectional antenna. STM32 microcontrollers are used in the drive system and robotic arm to enable motion.
The chassis of the rover is made of aluminum sigma profiles, which provide both strength and ease of assembly. Static balance is ensured by using rectangular profiles. A rocker bogie suspension system is used for the rover's movement. These systems allow the rover to traverse rough terrain while maintaining contact with the ground. The wheels are 3D printed using TPU material, while the rims are manufactured from ABS. Thanks to TPU, both flexibility and durability are achieved. The wheels are powered by DC motors. These motors were selected based on torque calculation to ensure that the rover can comfortably climb slopes of 30 to 45 degrees.
For dynamic systems, we integrate an AMU, stereo camera, 2D LiDAR, and in backup plans GPS. Autonomous driving algorithms are developed using software technologies like ROS, Arvis, and Gazebo. For mapping, we use a combination of SLAM techniques and global path planning algorithms. Specifically, we implement 2D LiDAR-based SLAM using tools like Gmapping and Cartographer for building accurate environment maps in real time. For navigation, we rely on the ROS navigation stack, utilizing algorithms such as Dijkstra and A-Star for global planning. These approaches allow the rover to dynamically adjust its path while safely navigating through unknown or complex terrain. For computer vision and image processing, we benefit from MATLAB provided by the competition and from libraries like OpenCV and YOLO. For manual driving, we developed a ground control station to ensure ease of control built using Python integrated with Qt framework. These tools helps us build a smarter and more adaptable rover, but we don't just use technologies, we analyze them deeply to implement each component in a smarter, more customized way on our rover. We care about building not just the code, but intelligent, reliable systems. While doing all this, we actively collaborate with other subteams from mechanical to electronics, creating a multidisciplinary space where ideas flow freely. This communication doesn't just build up our system, it boosts us as engineers.
The drone utilizes a CUAV autonomous flight controller running autopilot firmware for reliable waypoint navigation and dynamic in-flight adjustments. Four brushless motors, each controlled by a dedicated high-efficiency ESC, deliver consistent low-latency thrust. A 3-cell LiPo battery provides power, while an onboard power module both steps down and monitors voltage to safeguard the flight controller. For safety, the remote controller includes an emergency stop switch, allowing immediate motor shutdown in critical situations. This configuration achieves precise attitude control, robust performance under variable conditions, and endurance sufficient for extended field operations.
An autonomous drone system is being developed for a multi-step mission, including automatic takeoff, flight, area scanning, and precision landing. Designed for GPS-denied environments like indoors or ERC-style challenges, it relies on computer vision and sensor data. The mission begins with autonomous takeoff from designated spot marked by a marker. The onboard camera estimates distance based on a marker's apparent size, while barometric sensor provides continuous altitude data. Fusing both sources improves altitude accuracy and robustness. Post takeoff, the drone will search for the landing zone ARCA ID 102, randomly placed within 3-meter radius of the takeoff point. Detect and localize 3 stationary probes using image processing and object detection, mapping positions relative to reference or onto 1 by 1 meter grid. Throughout the mission, the drone will track the landing marker using visual and barometric data. Once it reaches the target height and meets the stability criteria, it will perform a precision landing. While optimized for GPS-free operation, GPS-based approaches are also being considered.
We use an STM32 microcontroller to control all the motors in our robotic arm. The motors operate at 24 and 12 volts, providing sufficient torque and speed for precise movement. The STM32 runs a PID controller that uses only desired joint angles, which are calculated through inverse kinematics. This architecture allows the system to automatically adjust motor's outputs to match the target current. By relying on inverse kinematics and closed-loop control, we significantly reduce the need for human interaction, making the robotic arm more autonomous and suitable for automated tasks.
The robotic arm is designed to be 1 meter long with 6 degrees of freedom. It's constructed using aluminum square box profiles, and the joints are connected with PLA parts. The movement of the base link and the second link is driven by a pulley belt system. The robotic arm operates using a combination of electrical motors. At the end of the robotic arm, a differential gear system consisting of bevel gears and ball bearing is used. These systems enable the gripper to move up and down, as well as rotate around its own axis, making it easier to reach and grab samples.
An easy-to-use interface card connected to the load cell was employed to measure the weight of the sample intended to be collected with the drill. After calibration, the system achieved a measurement uncertainty of just 1 gram.
An Archimedes screw mechanism is used in the drill system. This system converts the rotational motion into linear motion, allowing the soil sample to be easily lifted upwards.
We divided our work for science tests into 3 main headings. These are literature review, reporting, and Martial studies. For the literature review, we first used the ERC rulebook and then used recent articles written for wireless mariners. For the reporting part, we aim to critically discuss the information we obtained from the literature review. In addition, we use Adobe Illustrator and QGIS for mapping. We aim to understand the development of wireless mariners by utilizing general literature for Martial studies. Finally, we work with other subteams on scientific equipment on the rover for missions such as the pH test. With the help of sensors added the rover, we can measure factors such as the pressure, humidity, and temperature for Martial.